Hi, welcome to another video about Python, and this video is the part 2, how to solve the ordinary differential equations with initial conditions together with using the scipy.integrate solve IVP. And as you can see, this is the part 2. In case that you haven't seen the part 1, please watch it because it's like I introduced the basics of how to use this library to solve the ordinary differential equations with initial conditions. But in this case, I just continue with what I have said in the previous video by showing another example. And the difference between this video and the previous one is that in this video you will have a system of ordinary differential equations. Not only one equation, but you have at least two, so it's a system of equations. And moreover, in the previous video we only solved the first derivative equation. On the left side we have only first derivative. However, in this case we have second derivative. So what will be the difference? I will demonstrate the example, introduce some concept about the example before we go into the code. So let's see what are the examples that we're going to solve in this case. So the example so this is the example that I have from the computational physics book together with some information in the numerical methods in physics at the University of Jyvaskyla. So if you don't understand how can we have such a system of equations, please either you could derive them through some physics formula, or you can just read this book, Computational Physics, Mark Newman. I even say this is the example 8.8, space garbage. Please read it in order to understand how could they derive this system of ordinary differential equations. So our problem is that we have this ball. It will orbiting in the plane perpendicular to this steel rod, and our duty is to solve what does it look like when the ball moving in this plane. So the x will represent the x coordinate of the ball moving in this perpendicular plane to the rod at the center, and the y is the y coordinate. We need to find out the trajectory of the ball moving in this case when the ball only experiences the gravitational force between the ball and the rod without the gravitational force of the earth, like zero gravity from the environment. From all of those assumptions, all of those conditions, they derive this system of equations. So our duty again is to find the function of the x coordinate according to the term, and also the function of the y coordinate according to the term, and then we will plot it in the plane of xy in order to see the trajectory of the ball, whether it's a circle or something else. And so it's pretty clear. This is the system of ordinary differential equation that we need to solve. And G, M, or L, they are only constants. They defined inside the example. And about the unit, we don't care about the unit. In this case, let's assume all of the units in this example are standards. So we don't have to worry about the unit. We can focus on the main part is to solve this system of equations. However, we have here only the system of ordinary differential equations. We need to have the initial conditions. The initial condition is defined in this case at this point. I will change to the highlighter. Maybe it will be better. So this is our initial condition. At t equals 0, we have the position of the ball starts from x as 1 and y as 0. Together with at t equals 0, the velocity of the ball In the x coordinate is 0, and in the y coordinate is 1. This one is the second derivative. Why? Because the velocity is already the first derivative of the position. So here we have the second derivative. Because we're solving the second derivative, as a result, for the initial condition, not only we need to have the position values, but we need also the velocity values. We need to have the zero derivative of the variable and also the first derivative of the variable if the equation is about the second derivative. And okay, let's go to the code. So this is the code. This is exactly the code that I demonstrated in the part 1. In this video, I will start to modify this code according to our example. I put the example here. According to the example, we will modify this code and we will see the result. So first we need to run the necessary libraries. The run is successful. Define the input voltage. In our case, there's no input voltage, so it's not necessary. We can just delete it. And then here comes the very important part, which is the ordinary differential equations. But now we have the system. Would it be different? No, it would not be different. We also need to have a function where we need to pass in the independent variable and the y. The y is only a representative. Actually, it will be an array of variables. It's not only like the y coordinate. Please don't be confused with the y coordinate in our case. So in that case, I might change to some, let's say the name is k. Let's say it's k. So in the k, how can we know like what are these things the k will contain? Okay, let's look at the initial values. In our case, we need to solve what? We need to solve the second derivative. The second derivative, so it means that the initial value need to have the zero order derivative, which is the variable itself. Let's say, first consider the coordinate x. So the zero derivative of the x coordinate is x. And the first derivative of the x coordinate is the x velocity. But that's not it. What else do we need? We need to have the y coordinate and the y velocity. That's why we need to put it here, because it's not only an equation, a second derivative equation, but it's a system of secondary equations, differential equations. That's why we need to have x, vx, y, and vy. And let's pass in. So this is only a comment. I use those comments in order to remind myself what are these things going to pass inside this function, so I can easily put in the value here. So the value, initial value of x is, in our case, is 1. The initial values of velocity of x in our case is 0, and the y coordinate in this case is 0, and the y velocity is 1. So it's done, right? Come to our definition of function again. These initial values, somehow we have the same format with our k. So our k will be also x, velocity of x, y, and velocity of y. Let's define some constants that they used in this system of equations. They have g equal 1, m equal 10, L equal 2, and what else do we need? We need the r square root of the square x, the power, and the square y. Okay, now let's define our system of ordinary differential equations. If you look in the book of Computational Physics by Mark Newman, the system of ordinary differential equations is referred as the ordinary differential equations with more than one variable. It will be the same, more than one variable. In our case, it's more than one variable because we not only have x variable, but we, on the other hand, we have the y variable. That's why system ordinary differential equations has more than one variable. So now let's look at our main focus, which is the problem, the system. Now we need to define the system. So in the system, we have two equations. Let's define the first equation. So for the first equation, we have the second derivative of x, right? And we just have to type in the whole equation itself. Okay, if you pay attention, under the x variable, we have a very serious warning. X is not defined. Of course, x is not defined in the scope of the ODE function we define here, because we pass in only the t variable and the k. K is an array. So in our case, the k array will contain these values: x coordinate, velocity of x, y coordinate, and then the y velocity. It should be the same format with the initial values that we pass in. So what? So x here should not be x, it should be the k at the index 0. And the y should be the k at the index 2. And of course here we need to change also. Because this is the function. The function will be used by our solve IVP. And because we are solving the second derivative, that's why in the return we need to return the zero derivative and the first derivative. Okay, let's define the return value. The first is, sorry, I made a mistake, because we are solving the second derivative. So we need to return the first derivative and the second derivative. The second derivative, ddx and ddy, they are already defined in this step. Now we need to define the rest, which is the first derivative. The first derivative, we don't need to do anything else because we already passed this in, so it will be k at index 1, and dy will be k at the index 0, 1, 2, 3. Now we have x, then we need to return dx. Vx means dx, so we need to return second derivative x. Similarly for y. Okay, let's run and define the function. Good. Now we run for the initial values. Good. Now we will solve the function. So in this case, we pass in our function and then we pass in the interval of the independent t variable in order to solve it, because we have the position dependent on the time. We need to solve from the time 0 to the time, let's say 10. Initial value is initial value, and the method that they will use will be the RK45. It's done. Let's solve it. Good. Now we will. Do we need to check this one? We don't need to check this one. It's not necessary. I just demonstrated in the last video for some demonstration. But I will have a note here. So this is my note about what will be returned for the result here. So because the y attribute will be an array, and that array contains 4 things. It contains the values for the x position, the values for the velocity x, the values for the y position, and the value for the velocity y. Even though in this case we only need to solve the values of the x and the y positions. However, because this solver is defined by the function, it's already defined before we use it, and the way that it's defined is that it returns all of the variable, not only for the position, for the zero derivative, but also for the first derivative, because we are solving the second derivative. That's why it will return the lower derivatives in this case, which is the zero derivative and the first derivative. Now let's plot. So in the figure number 1, I will plot the x position with the time together with the plot of the y position with the time. This is the x position is the blue plot, and the yellow or the orange plot is the y position. And this is the position dependent on the time. Let's plot the x and the y on the plane. We will plot, I put the problem here again. If you could see, the ball is moving in a plane perpendicular to the rod at the center. So we want to know like the shape or the trajectory on that plane, on that perpendicular plane. I will plot in another figure. This is how it looks like for the trajectory of the ball. As you intuitively imagine, it's not a circle. This is like the real trajectory of the ball going in the plane perpendicular to the rod at the center. It's like a flower. It's not a circle. And on the x-axis, it shows the x position, and on the y-axis, it shows the y position. You need to pay attention to the position of the variable that you need to plot. If you want to plot on the x-axis is the x position, then you need to put this variable. And if you want to make sure on the y-axis is the y position, you need to make sure that the second variable you pass in is this one. Show only some feature when we use the solve IVP. What is the feature? The feature is that we can decide at what time points or at what independent variable we want to compute our solution. In this case, we haven't specified to the solver at what point, at what time point we want the solve IVP to return our value. That's why they will return the value at a very random time. Let's compare. So this is the solver decide randomly at what time point they will compute the results. But in this case, the second case, we will decide. We will be the one to tell the solver I want you to return the value at those specific time points. Let's generate. In case you don't know, like, what is the purpose of using a linspace? A linspace is a function to return automatically generated array from 0, let's say, to 10, but the number of points will be 1000. So the interval between each point are equal. And now we have just tell the solver that we want the solver to return at the time point we defined in this variable teval. Okay, let's run. And let's compare the results returned by the solver at random time point and the solver when we tell the solver to return at a specific time point. I will modify this one to solve to and solve to 0. It has the same x coordinate. For this one, when the time interval is randomly, let's say it's the blue marker as a circle, and this one has a red with the plus. Now let's see. Yeah, I forgot the comma. It's not too clear, right? Let's make the number of points to be smaller, make it 10. Let's say 9. And here we plot it again. Okay, let's change it to a marker circle too. Okay, now you could see the difference easily. So the blue dots are the one returned by the solver at a very random time point. However, when we tell the solver, in this case, to return at those specific time point, and the solver exactly return according to our demand. So have only 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 red dots as we expect the solver to generate. And I just want to show this attribute of the solver. So in case that maybe we want to do something, we can utilize this kind of attribute of the solver IVP. And thank you so much for watching the video. If you find that the video is somehow helpful, please give me a like or subscribe. Or if you have you find out something wrong in my video, please, I am open to your feedback. Thank you so much for watching, and see you